So in this chapter, you're going to learn all about alkenes and addition reactions. So here's a brief outline of this chapter. We're going to talk about alkenes and what they are in general. At this point, you should already have a pretty good idea of what they are. And we're also going to cover degrees of unsaturation and how they can help us predict molecular structures. And then you're also going to learn how to name alkenes, the different types of alkenes, their properties, how to prepare them, what kind of chemical reactions, and the different types of chemical reactions that they undergo. So there's hydrohalogenation, hydration, halogenation, and then we're also going to cover halohydrogen formation, and finally hydroboration and oxidation. So alkenes are considered unsaturated hydrocarbons because they contain a carbon-carbon double bond. In the oil industry, alkenes are also known as olefins. And there's a lot of different types of olefins. There's a terminal alkene, internal alkene, and cycloalkene. In a terminal alkene, the double bond is at the end of the carbon chain, whereas in an internal alkene, the double bond is within the carbon chain. And finally, in cycloalkene, the double bond is inside a ring, a cyclic ring. So if you remember, a carbon-carbon double bond contains two different types of bonds, a sigma bond and a pi bond, according to the valence bond theory. In this theory, both carbon atoms that are involved in the double bond are sp2 hybridized with a trigonal planar geometry and bond angles of about 120 degrees. The pi bond is oriented above and below the plane, whereas the sigma bond is oriented within the plane. In terms of energy, pi bonds are actually weaker compared to sigma bonds within the same carbon-to-carbon double bond, and that's why they're a lot easier to break compared to sigma bonds. The strength of the pi bond can easily be estimated by comparing the bond dissociation energy of an alkene from that of an alkane with the same number of carbon atoms. So let's take a look at ethylene and ethane, for example. They both have the same number of carbon atoms. The only difference is one contains a pi bond and the other doesn't. So here you can see that it would require 635 kilojoules per mole of energy to break this double bond in ethylene, whereas in ethane, it would only require 368 kilojoules per mole of energy to break this single bond. And if we take the difference between the two energies here, we get the energy of the pi bond only. And you can see that this energy is less compared to the energy of the sigma bond. And that's why pi bonds are easily broken in a lot of chemical reactions. And so this is one of the main reasons why alkenes undergo many reactions that alkanes do not. In terms of alkenes within a ring, cycloalkenes with less than 8 carbon atoms actually prefer having a cis geometry. So here we have cis cyclooctane with 8 carbon atoms. You can see that we have a cis geometry here because the 2 carbon atoms are on the same side of the double bond. Whereas in trans cyclooctane, the 2 carbon atoms are on the opposite sides of the double bond. So that means that cycloalkenes with less than 8 carbon atoms are more stable, having a cis geometry, than trans geometry. A trans cycloalkene must have a carbon chain long enough to connect the ends of the double bond without introducing too much strain. And so the trans cyclooctane is actually the smallest isoluble trans cycloalkene, but it's still actually considerably less stable compared to a cis cyclooctane, making it one of the few alkenes having a higher energy trans isomer. So here's a table that basically summarizes the different properties of the carbon-carbon double bond. So you already know that double bonds have restriction on their rotation, and the reason why is because of the presence of the pi bond. So the only time that you can rotate around a double bond is if you were to break that pi bond. In terms of stereoisomerism, whenever you have two different groups on each end of the double bond, then a cis and trans isomers are possible. And in terms of stability, the more substituted the double bond is, the more stable they are. And so the stability of an alkene increases as the number of R groups on the double bond increases. And also, generally, trans alkenes are more stable compared to cis alkenes. And again, the only exception here is if you have a cycloalkene with less than 8 carbon atoms. In that case, the cis geometry dominates. So the degrees of unsaturation of a molecule can basically help us identify and predict whether its structure contains a pi bond, a cyclic ring, or a combination of both. So for the first 3 bullet points here, you should already know regarding alkenes. an acyclic alkene has the general formula CnH2n. So that means that you have 2 hydrogen atoms per carbon atom. And so if you have a total of 5 carbon atoms within the alkene, then that means that you have a total of 10 hydrogen atoms. Alkenes are considered unsaturated hydrocarbons because they have less than the maximum number of hydrogen atoms per carbon. Cycloalkanes also have the same general formula as an acyclic alkene, which is CnH2n. So you can see here that both acyclic alkenes and cycloalkanes have 2 hydrogen atoms less compared to a saturated alkane with the same number of carbon atoms. That means that each pi bond or ring removes 2 hydrogen atoms from a molecule, and this introduces 1 degree of unsaturation. So how do we determine the number of degrees of unsaturation for a given molecular formula? Well, we can calculate that by simply comparing the actual number of hydrogen atoms of that compound to the number of hydrogen atoms of a saturated alkane with the same number of carbon atoms. And once we've identified the number of degrees of unsaturation for a given molecular formula, then we'll be able to know the total number of rings and or pi bonds within that molecule. So if a compound contains 2 degrees of unsaturation, that means its chemical structure contains either 2 rings, 2 pi bonds, or a combination of 1 ring and 1 pi bond. So here's an example. Calculate the number of degrees of unsaturation in a compound of molecular formula C4H6 and propose possible structures. So in order to calculate the number of degrees of unsaturation, the first thing that we want to do is to determine the maximum number of hydrogen atoms in a saturated alkane with the same number of carbon atoms. And so since we have 4 carbon atoms, that means that the maximum number of hydrogen atoms can be calculated using this formula here. So 2n plus 2, in which n is the total number of carbon atoms. And so substitute that for n. So 2 times 4 is 8 plus 2, and we get a total of 10 maximum hydrogen atoms. And so now to calculate the number of degrees of unsaturation, all you have to do is take the difference between the maximum and the actual number of hydrogen atoms, and then divide that by 2. So here we have 2 degrees of unsaturation. So since we have 2 degrees of unsaturation, there are 3 possible structures here. You can have, the structure can have 2 rings. It can contain 2 bonds or 2 pi bonds, or a combination of the 2. So 1 ring and 1 pi bond. And for the first one here, we can have 2 rings with 4 carbon atoms and 6 hydrogen atoms. And then for the second one, we can have 2 pi bonds. We can have 2 possible structures. You can see that we have 2 pi bonds here with a total of 4 carbon atoms and 6 hydrogen atoms. In the second structure here, this triple bond contains 2 pi bonds as well. And you can see that it contains a total of 4 carbon atoms and 6 hydrogen atoms. And then finally, we can have a ring and a pi bond. So it's a combination of a ring and a pi bond. So you can see that we have 4 carbon atoms here in a ring and contains a pi bond. Here's practice problem number 2. Calculate the number of degrees of unsaturation for each molecular formula and propose 2 possible structures. So for the first one here, we have C8H12. So we have a total of 8 carbon atoms and 12 hydrogen atoms. And so we can calculate the number of degrees of unsaturation by calculating or determining the maximum number of hydrogen atoms possible per carbon atom. And so if we have 8 carbon atoms, we can use this formula here to calculate the maximum number of hydrogen atoms. And so 2 times 8 plus 2, and we get 18 maximum hydrogens. And so now we can take the difference between the maximum and the actual number of hydrogen atoms divided by 2. And if we do that, we get 3 degrees of unsaturation. So for the first one, we can have 3 rings. So you can see that we have a total of 3 rings here. And when you count the total number of carbon atoms and the number of hydrogen atoms, it checks out. All right. And we can also have 1 ring and 2 pi bonds within the structure. So here's a ring and 2 pi bonds. So you can have 2 double bonds here and a ring containing 4 carbon atoms. So again, when you count the total number of carbon atoms here and hydrogen atoms, it should equate to 8 carbons and 12 hydrogens. So for the next one here, we have C10H10. And so we have a total of 10 carbon atoms and 10 hydrogens. So the very first step here is to calculate the maximum number of hydrogens for the same number of carbon atoms. And so 2 times 10 carbon atoms plus 2, and we get 22 maximum hydrogens possible. And so now we can take the difference between the maximum and the actual number of hydrogen atoms divided by 2, and we get 6 degrees of unsaturation. And so with 6 degrees of unsaturation, we can have a structure with 6 pi bonds. We can have 6 rings, or a combination of pi bonds and rings. So I chose 5 pi bonds and 1 ring. So with 6 pi bonds, you can have this structure shown here. So you can have a combination of double bond and triple bonds. So this triple bond here contains 2 pi bonds. So we have 2, 3, 4, 5, 6 pi bonds. And again, you can count the number of carbons and hydrogens, and it should equate to 10 carbons and 10 hydrogens. And for the second structure here, we can have 5 pi bonds and 1 ring. And so this structure here shows you a ring with 3 pi bonds plus 2 pi bonds outside the ring. And what about for molecules containing heteroatoms? How do we calculate the degrees of unsaturation for these molecules? So here are some of the steps that you can follow in determining or calculating the degrees of unsaturation for these kind of molecules. When it comes to oxygen atoms, ignore them. Ignore the oxygen atoms. They have no effect on the degree of unsaturation. When it comes to halogens, add the number of halogens to the number of hydrogens. So they're essentially equivalent to hydrogen atoms. When it comes to nitrogens, you're going to subtract 1 hydrogen for each nitrogen present. And so here's an example. We have C6H10, OCl3, nitrogen. So you can see that we have 10 hydrogens here. We're going to ignore the oxygen atom and then add 3 to the existing 10 and then subtract 1 because of the nitrogen. So this molecule has essentially the same degrees of unsaturation as C6H12. So here's an example. Calculate the number of degrees of unsaturation for each molecular formula. So for the first one here, we have C5H8O. So we have a total of 5 carbons and 8 hydrogen atoms. So for the oxygen atom, we can ignore this because it has no effect on the number of degrees of unsaturation. And so again, the very first step here is to determine the maximum number of hydrogen atoms possible for 5 carbons. And so 5 times 2 is 10, plus 2 equals 12. So the maximum is 12 hydrogens. And then we're going to take the difference between the maximum and the actual number of hydrogen atoms divided by 2. So 12 minus 8 divided by 2 equals 2. So that means we have 2 degrees of unsaturation. And so the structure should contain either 2 rings, 2 pi bonds, or a combination, 1 ring and 1 pi. So here's the one that I chose. The oxygen atom is part of the ring, and you can see that we have a total of 1, 2, 3, 4, 5 carbon atoms with 1 double bond or 1 pi. So a ring and a pi would count as 2 degrees of unsaturation. And for the second one here, we have C6H11 and 1 chlorine. So we have 6 carbon atoms, 11 hydrogens, and 1 chlorine atom. And so we're going to count 1 chlorine as 1 hydrogen. And so that means that we have 12 hydrogens total here. And so again, we're going to count or calculate the maximum number of hydrogens possible. For 6 carbon atoms, 6 times 2 is 12, plus 2 equals 14. So 14 maximum hydrogens. And then we're going to take the difference here. 14 minus 12 divided by 2 equals 1. And so for this specific molecule, we only have 1 degree of unsaturation. And so you can draw, we can use this structure right here, which is basically a cyclohexane with a chlorine attached to the ring. And so we have 1 ring here, which counts as 1 degree of unsaturation. And for the third one here, we have C8H9 and 1 nitrogen. So we have 8 carbons, 9 hydrogens, and 1 nitrogen. So we have to subtract one hydrogen for every one nitrogen present. And so that means that we have a total of 8 hydrogens here. And for the maximum number of hydrogens, there's 18, because we have 8 carbons. 8 times 2 is 16, plus 2 equals 18. And now we're going to take the difference between the two hydrogen numbers of hydrogen atoms here. So 18 minus 8 equals 10. Divided by 2, we have 5. So we have 5 degrees of unsaturation for this molecule. So here's the structure with 5 degrees of unsaturation. We have a nitrogen within a ring. So one ring is 1 degree of unsaturation, and then a total of 1, 2, 3, 4 pi bonds. So that's a total of 5 degrees of unsaturation. So here's practice problem number 3. How many degrees of unsaturation are present in each compound? So for the first one here, we have C6H6. So we have 6 carbon atoms and 6 hydrogens. And so the maximum number of hydrogens possible for this compound with 6 carbons is 6 times 2 equals 12, plus 2 equals 14. So we have 14 hydrogens maximum possible. And so the next step here is to take the difference between the two numbers here, 14 minus 6, and then divide that by 2. So 14 minus 6 divided by 2, and we get 4 degrees of unsaturation. And for the next one here, part B, we have C8H18. So we have 8 carbon atoms and 18 hydrogen atoms. And to get the maximum here, we multiply the number of carbon atoms by 2 and then add 2. So we have 8 times 2 equals 16, plus 2 equals 18. So we already have the maximum number of hydrogen atoms for this specific molecule. We already have an alkane, which is considered a saturated hydrocarbon. And so in that case, we get 0 degrees of unsaturation. So this is already a saturated hydrocarbon. And for part C here, we have C7H8O. So we have 7 carbon atoms, 8 hydrogens, and 1 oxygen. And so with oxygen atoms, we can just ignore them because they don't play a part in the degree of unsaturation. And so the maximum number of hydrogen atoms here is 7 times 2 is 14, plus 2 equals 16. So 16 maximum hydrogens. Subtract that by 8 and divide it by 2. And we get 4 degrees of unsaturation. And for part D here, we have C7H11Br. So we have 7 carbon atoms, 11 hydrogen atoms, and 1 bromine. And so in order to calculate the maximum number of hydrogens here, we multiply 7 by 2. So 7 times 2 is 14, plus 2 equals 16. So we have 16 maximum hydrogens. And then we're going to subtract, or we're going to add 11 and 1, because bromine basically counts like a hydrogen atom. So 11 plus 1 is 12. So subtract 12 from 16 and divide that by 2, and we get 2 degrees of unsaturation. And then finally, we have C5H9 and 1 nitrogen. So we have 5 carbon atoms, 9 hydrogens, and 1 nitrogen. So the maximum number of hydrogens here is 12. And then we're going to subtract 1 from 9, because nitrogen, we have to subtract 1 from hydrogen for every 1 nitrogen. And so in that case, we have 8 hydrogens here. So 12 minus 8 is 4, and divided by 2, and we get 2 degrees of unsaturation. And here's another practice problem. How many degrees of unsaturation does each of the following drugs contain? So the first one here is zolpidem, which has the chemical formula C19H21N3O. So we have 19 carbon atoms, 21 hydrogens, 3 nitrogens, and 1 oxygen. And so the maximum number of hydrogens possible here would be 19 times 2 plus 2 equals 40. So we have 40 maximum hydrogens possible. And to calculate the degrees of unsaturation, we're going to subtract 21 from 40, as shown here. So we're also subtracting 3 nitrogens, because again, nitrogen, we have to subtract 1 from hydrogen for every nitrogen present. And so since we have 3, we're going to subtract 3 from 21, and then subtract that from the maximum, which is 40. So in this case, 40 minus 21 minus 3 divided by 2, and we get a total of 11. So this is 11 degrees of unsaturation. And for the second one here, we have mifloquine, which has the chemical formula C17H16F6N2O. So we have 17 carbon atoms, 16 hydrogens, 6 fluorines, 2 nitrogens, and 1 oxygen. So the oxygen, we can just ignore that, but we have to subtract 2 nitrogens from 16 hydrogens, and then add 6 fluorines, because fluorines basically count like hydrogens. And so the maximum number of hydrogens here is 36. 17 times 2 plus 2 equals 36. And then calculating the degrees of unsaturation here, we're going to subtract the maximum, or take the difference between the maximum and the number of hydrogens. So again, we have 16 hydrogens. We're going to add 6 because of the fluorine atoms, and then subtract 2 because of the nitrogens. And then subtract all of this from the maximum and divide that by 2, and we get 8 degrees of unsaturation. So now let's take a look at the rules regarding naming alkenes. So how do we name an alkene using the IUPAC system? So here's an example. You can see that we have a double bond here between these 2 carbon atoms. And the very first step here is to find the longest chain that contains both the carbon atoms of the double bond. And so in that case, our longest chain here would be this one right here. All right, so count the total number of carbon atoms here. We have 1, 2, 3, 4, 5, and 6. So that means that we're going to have a hexene here because of 6 carbon atoms. And then step number 2 here says number the carbon chain to give the double bond the lower number, and then apply all the other rules of nomenclature. And so the double bond is right over here. And so we're going to label the carbon atoms from left to right so that it'll give the double bond the lower number. And so we have 1, 2, 3, 4, 5, and 6. So you can see that we have the double bond on carbons 2 and 3. And so once you've numbered the carbon chain to give the double bond the lower number, we're going to apply the other rules of nomenclature. And so we're going to name this hex, and then the number 2, and then ENE. So the number 2 here indicates that the functional group, the double bond, is on carbon number 2 and 3. So we're going to use the lower number, which is 2 instead of 3 here, in naming this alkene. So we have a hex 2 ENE, or hex 2 ene. And then finally, we're going to name the substituents. So you can see that we have 1, 2, 3 methyl groups here. So it's going to be on the 2nd carbon atom, the 3rd carbon, and the 5th carbon atom. So we have a 2, 3, 5 trimethyl. So that is 2, 3, 5 trimethyl hex 2ene. So whenever you're naming an alkene, you always want to make sure that whenever you're finding the longest chain, to include both carbon atoms that are involved in the double bond. So for example, over here, even though the longest chain contains 8 carbon atoms, this would be incorrect because you didn't include both carbon atoms that are involved in the double bond. So the correct way to name this would be this one right here on the left, in which the double bond, or both carbon atoms in the double bond, are part of the longest chain. And so the correct name for this is 2-ethyl hept 1-ene. So again, that's 2-ethyl hept 1-ene. So a lot of organic compounds can contain multiple functional groups, but compounds that contain both a double bond and a hydroxy group are called alkenols, and the chain or ring is numbered to give the hydroxy group the lower number. So in that case, the hydroxy group gets the higher priority over the double bond. So here are 2 examples of alkenols. You can see that they both end in enol. The suffix is enol, E-N-O-L, and the hydroxy group gets the higher priority, so it has the lower number. So it ends in 1-OL, and then you can see that the double bond here is numbered 2, right? So it's 2-EN, 1-OL. Same thing over here. You can see that the hydroxy group gets the higher priority, so it gets the lower number. And then the alkene group, the double bond here, is on the 6th carbon atom. So that would be 6En2OL. So how do we name cyclic alkenes and alkenes containing multiple double bonds? So here are some of the rules that you can use whenever you're naming these type of alkenes. So the first one here says compounds with 2 double bonds are named as dienes by simply changing the A and E ending of the parent alkane to the suffix adiene. Compounds with 3 double bonds are named as trienes and so forth. And in naming cycloalkenes, the double bond is located between C1 and C2, and the 1 is usually omitted in the name because, again, you have a cyclic ring. The ring is numbered clockwise or counterclockwise to give the first substituent the lower number. So let's take a look at a few examples here. So here we have a cyclopentene ring in which the first substituent is bonded to the first carbon atom. And so here we have 1-methyl cyclopentene. And then the next one here, we have a cycloheptene with 7 carbon atoms. And again, the double bond is labeled as the first carbon. And so we're going to label the carbon atoms clockwise to give the second or the first substituent here the next number. And so that would be 1, 2, 3. And so we have a 3-methyl cycloheptene. And then for the third one here, we have a cyclohexene because we have a total of 6 carbon atoms in a ring. And then we're going to number the first methyl group here as the first substituent. So we have 1, 2. So we're numbering the carbon atoms counterclockwise this time. So that's 1, 2, 3, 4, 5, 6. So we have a methyl group bonded to the first carbon atom and then another one on the 6th carbon atom. So when naming this ring here, we have 1,6-dimethyl cyclohexene. So here's practice problem number 5. Give the IUPAC name for each alkene. So for the first one here, we have this longest chain which contains 5 carbon atoms, including the double bond. And so this is going to be a pentene, in which the double bond is on the first carbon atom. So this is going to be labeled from left to right, 1, 2, 3, 4, and 5, in which the double bond again is on the first carbon atom. And so this is going to be a pent-1-ene. And then you can see that we have a methyl group bonded to the third carbon atom. And so the compound's name is going to be 3-methyl pent-1-ene. And for the second one here, this is our longest chain. You can see that there's a total of 7 carbon atoms, again, which includes the double bond. And the double bond is going to be on the 3rd and 4th carbon atom. So again, you want to minimize the number of the double bond. So instead of counting from right to left, it's going to be from left to right. So in this case, since we have 7 carbon atoms, this is going to be a hept-3-ene. Hept-3-ene. And then on the 3rd carbon atom, there's an ethyl group. And so in that case, the name of this compound is going to be 3-ethyl hept-3-ene. And for part C here, again, we have to include the double bond. And so the longest carbon chain would contain 1, 2, 3, 4, 5 carbon atoms. And so the double bond is between carbons 1 and 2. And so we're going to label this from left to right. So in that case, this is going to be a 5 carbon chain. So we have pent-1-ene. It's going to be a pentene, pent-1-ene. And then you can see that we have a ethyl group on the 2nd carbon and then a methyl group on the 4th carbon. And so ethyl goes first before methyl. And so that's going to be 2-ethyl 4-methyl pent-1-ene. For the 4th molecule here, you can see that we have a cyclic ring containing 5 carbon atoms. And so this is going to be a cyclopentene. And we're going to label the carbon atoms clockwise so that the first substituent gets the lower number. And so starting from the double bond, so we have 1, 2, 3, 4, and 5. And then notice that we have 2 methyl groups, one on the 3rd carbon atom and another one on the 4th carbon atom. And so what we have here is 3,4-dimethyl cyclopentene. Again, if you have a cyclic ring, you don't have to include the 1 because it's already implied because it's a cyclic ring. And so what we have here is 3,4-dimethyl cyclopentene. And for the last molecule here, you can see that we have another cyclic ring containing a total of 6 carbon atoms. And so what we have here is a cyclohexene. And then we're going to label the carbon atoms starting with the double bond that's also connected to a methyl group. And so this is going to be our carbon 1 right here, followed by carbon 2. And so we're going to label the carbon atoms clockwise. Carbon 5 and then carbon 6. And you can see that we have 2 substituents connected to the ring. We have a methyl group on the first carbon atom and then a tert-butyl group connected to the 5th carbon atom. And so when naming this compound, we have tert-butyl. So this is 5-tert-butyl, 1-methyl. So remember to alphabetize the substituents. So again, that's 5-tert-butyl, 1-methyl cyclohexene. So again, that's 5-tert-butyl, 1-methyl cyclohexene. And here's another practice problem. Give the IUPAC name for each polyfunctional compound. For the first molecule here, you can see that we have 2 functional groups. We have the hydroxy group and the alkene group. And so this is an enol, a compound containing a hydroxy group and a double bond. The hydroxy group gets the higher priority, and so we have to label this carbon atom that's connected to it carbon number 1. And so this is carbon number 1, 2, 3, 4, 5, and 6. So again, we have to include the double bond within the longest chain. So again, we have to label this from right to left, in which the carbon that's bonded directly to the hydroxy group gets the lowest number. And so in this case, we have a hexenol. Okay, so we have the hydroxy on the first carbon atom, and then the double bond on the 3rd and 4th carbon atom. So what we have here is hex 3-ene-1-ol. So that's a hex 3-ene-1-ol. And then notice that on the 4th carbon atom, we have an ethyl group. So this is a 4-ethyl hex 3-ene-1-ol. And for the second molecule here, we have the same thing. We have a hydroxy group and a double bond. And so this is going to be an enol compound. And we have to label the carbon atoms from left to right so that the hydroxy group gets the lower number. And so we have 1, 2, 3, 4, 5, 6, 7, 8. Again, the double bond has to be included within the longest carbon chain. And so again, that's 1, 2, 3, 4, 5, 6, 7, and 8. And so in that case, we have an octenol with 8 carbon atoms. So that's oct7-ene-4-ol. Okay, so again, that's oct7-ene-4-ol. And we have 2 substituents here, one on the 5th carbon atom and another one on the 6th carbon atom. So this is 5-ethyl, 6-methyl, oct7-ene-4-ol. And for the last molecule here, you can see that we have 2 double bonds. So this is going to be a diene. And the longest carbon chain is going to be 1, 2, 3, 4, 5, 6, 7. So we have a heptadiene. And notice that we have 2 methyl groups. So we can label this carbon atom from left to right or from right to left. It doesn't matter because the distance between the first carbon atom and the double bond is similar on both sides. And so we can just label this from left to right. And so you can see that we have a methyl group on the 2nd carbon and on the 6th carbon atom. And so this is going to be hepta 2,5. So again, that's hepta 2,5 diene because you have 2 double bonds here, starting from the 2nd carbon atom and another one on the 5th carbon atom. And then for the substituents, we have 2,6-dimethyl. So that's 2,6-dimethyl. So for the entire compound, the name is 2,6-dimethyl hepta-2,5-diene. So alkenes can have diastereomers known as cis and trans isomers. A cis isomer is when you have the two alkyl substituents on the same side of the double bond, whereas a trans isomer is when you have the two alkyl substituents on opposite sides of the double bond. So here we have cis hex 3-ene, in which the two substituents are on the same side of the double bond, and here we have trans hex 3-ene, in which the two substituents are on opposite sides of the double bond. And one important information that you should remember is that the cis and trans isomerism only works for disubstituted alkenes. So it doesn't work for trisubstituted or tetrasubstituted alkenes. And so we have to use a different method in identifying these alkenes, as you shall learn in the next few slides. So for trisubstituted and tetrasubstituted alkenes, we have to use the E and Z configuration. And so we have to assign the prefixes E and Z to the alkene. So how exactly do we assign the prefixes E and Z to an alkene? So the first step here is to assign priorities to the two substituents on each end of the carbon-carbon double bond by using the same priority rules for the R and S nomenclature. So looking at this first example here, you can see that we have this double bond here, and we have the two carbon atoms involved in the double bond. So the very first step here is to split this double bond in half so that we have the left-hand side and the right-hand side. And then we're going to assign priorities to the two substituents bonded to the carbon atoms. So for the one here on the left-hand side, the methyl group gets the higher priority, and then the hydrogen the lower priority. And we'll do the same thing on the right-hand side. We have a methyl group versus an ethyl group. So the longer carbon chain will receive the higher priority, and then the methyl group the second priority. And then we'll move on to the next step, in which we are going to compare the positions of the substituents. And for the second step, we're going to assign E or Z based on the location of the two higher priority groups. If the two higher priority groups are on the opposite sides of the double bond, then it's going to be an E isomer. If the two higher priority groups are on the same side of the double bond, then it's going to be a Z isomer. So here you can see that we have the two higher priority groups on the opposite sides of the double bond, and so we have an E isomer. So we have E3-methyl-pent-2-ene. And for the second one here, we have both the higher priority groups on the same side of the double bond, and so this is going to be a Z isomer. So here we have Z3-methyl-pent-2-ene. And here's practice problem number 7. Label each carbon-carbon double bond as E or Z. So for the first one here, the first thing that you want to do is to divide the double bond into half. So now we have the left-hand side and the right-hand side of the double bond. And then the next step here is to assign the priorities of the substituents bonded to the carbon atoms. And so for the first one here, the methyl group gets the higher priority. And then on the second half here on the right-hand side, the bromine atom gets the higher priority because it has a higher atomic number. And so you can see that the two higher priority groups are on the opposite sides of the double bond. And so what we have here is the E isomer. And for the second molecule here, we'll do the same thing. So we're going to split the double bond into half. So we have the left-hand side and the right-hand side, and then assign priorities. So you can see that the ethyl group gets the higher priority over the hydrogen atom here. Same thing for the ethyl group here versus the methyl group. Since the ethyl group is larger compared to the methyl group, it gets the higher priority. And so since both higher priority groups are on the same side of the double bond, what we have here is the Z isomer. And for the third molecule here, again, we're going to split this into half. So on the left-hand side, we have the isopropyl group as the higher priority. And then the sec-butyl group would have the higher priority over the ethyl group. And so you can see that the two higher priority groups are on the opposite sides of the double bond. And so what we have here is the E isomer. And for the last molecule here, you can see that we have two double bonds. So we have a diene. For the first double bond here, again, the very first step that you want to do is to split it in half. and then compare the substituents. So for the first one here on the left hand side, you can see that we have a methyl group versus a methoxy group. So the oxygen atom gets the higher priority. And for the right hand side, this side of the molecule gets the higher priority over the hydrogen atom. And then for the second double bond here, again, we have the left and right hand side here. For the left hand side, this side of the molecule gets the higher priority. And then for the right hand side, we have two groups here. The one up top is an ethyl group versus a methyl group. So the ethyl group gets the higher priority. And so now when assigning E and Z configuration here for the first double bond, you can see that the two higher priorities are on the opposite sides of the double bond. And so what we have here is the E isomer. And then for the second double bond here, you can see that both the higher priority groups are on the same side of the double bond. So what we have here is the Z isomer. And here's another practice problem. Draw the structure corresponding to each IUPAC name. So for the first one here, we have Z4-ethyl-hept-3-ene. So the first thing that I would do here is to draw the double bond. So here's our double bond, and it tells us that the double bond is on the third and fourth carbon atom. So we can label these two carbon atoms 3 and 4. And then the next step that I would want to do here is to draw the rest of the molecule. So we have, we're going to have carbons, or actually we can look at the ethyl group here. So it tells us that the ethyl group is on the fourth carbon atom. So here's our fourth carbon atom. So we can go ahead and draw the ethyl group, which contains two carbon atoms, and then the rest of the molecule. So for the fourth carbon atom, we have carbons 5, 6, and 7 bonded to the fourth carbon atom. And then it tells us that this is a Z isomer. So that means that we have to assign priorities. So we know that this group right here gets the higher priority because it's longer than the ethyl group. So this is our first priority here. And then for the left-hand side, the third carbon atom is going to be bonded to an ethyl group, the first two carbon atoms. And the first two carbon atoms should have a higher priority over the hydrogen that's also bonded to this third carbon atom. So let's draw the first two carbon atoms here. And so you can see that this gets the higher priority over the hydrogen atom. And so now we have the two higher priority groups on the same side of the double bond. So what we have here is the Z isomer. For the second molecule here, we have E356 trimethyl-octuene. Again, the very first thing that I would do here is to draw the double bond. And so here it tells us that the double bond is on the second and third carbon atom. So we can go ahead and label these two carbon atoms as 2 and 3. And then draw the rest of the molecule. So we have an octene here. So we should have a total of 8 carbon atoms in the longest chain. So we have a total of 8 carbon atoms. So we have 3, 4, 5, 6, 7, and 8. All right, and then it tells us that we have 3 methyl groups on the third, fifth, and sixth carbon atoms. So we have the third carbon atom here, fifth, and sixth. So we should have a methyl group bonded to these carbon atoms. And so you can see that on the right-hand side of the double bond, carbon number 3 here, it contains the higher priority group shown here. So this is a higher priority over the methyl group. All right, and then it tells us that we have an E isomer here. So that means that the two higher priority groups should be on the opposite sides of the double bond. So that means that the methyl group here will be on the opposite side of the double bond, as shown here. So again, the methyl group receives a higher priority over the hydrogen atom right here. And so what we have is an E isomer. And for the last molecule here, we have Z2-bromo-1-iodo-hex-1-ene. So again, the first thing that I would want to do here is to draw a double bond. And you can see that the double bond is on the first and second carbon atoms, as shown here. And then I'm going to go ahead and draw the rest of the molecule. So you can see that we have a hexene. So that means we have 6 carbons on the longest chain. So here's my longest chain here. We have carbons 3, 4, 5, and 6. And then on the second carbon atom, we also have a bromine atom. So here's the bromine atom. And you can see that the bromine atom has higher atomic number than the carbon atom, and so it would have the higher priority. And since we have a Z isomer here, the iodine, which is bonded to the first carbon atom, will be on the same side as the bromine atom because it has a higher priority over the hydrogen atom that's bonded to this first carbon atom. So this is the structure for the molecule Z2-bromo-1 iodohex-1-ene.